Hi everyone. So in this video we will be continuing our series and I will be talking about we will be taking a next step from the last video that was single leader databases, right? So just to recap, I want to draw what a single leader database kind of an architecture looks like, right? So basically, let's imagine that this whole database thing is for users just in the US right now. Okay, so this is our okay. So this represents a region basically, right? Let's say that we have a database, and this is this is the master. Let's call it the primary, right? And there are some replicas as well that we have. Let me copy this. Let's say, yeah. So we have three replicas and we have a primary DB. Let's call this R1, R2, R3. Here R stands for replicas, okay? And let's say that we have a user over here. So this user is actually a person of the US, right? Okay. So what would happen in this whole case is that this user will, let's say there's an application, right? Usually what we have learned is that writes are usually written to primary databases and reads are done from the replicas, right? So this user will basically write to this primary DB. This primary DB will, oh, 1 second, dude. This primary DB will then like stream those changes across the replicas. And what would happen is that this is basically what a single leader system looks like, right? Let's say this latency is around 2 milliseconds. So it takes 2 milliseconds for the user to write to this primary DB, right? All's good till here, right? This would serve very well to people who live in the US, for example. But let's try to think if we take our app global. Let's assume that there is, a user. Now, this is an Indian user, right? If we think about there's just a single leader and that is hosted in the United States, and this user wants to write to that DB, right? What would this person need to do? Well, this person will need to write to this primary DB as well, right? And this could take like 200 milliseconds, for example, right? This is 10 times the time this user will spend than a person who's in the US, right? And of course this is not feasible, right? I mean, why would we want our Indian users to take 10 times the time to write to the same DB? So there is a clear problem over here, right? If we have just one reader and that's in the US, it is going to take this, the UI would be pretty bad for these Indian users, right? So what we can do in a case like this is actually quite simple. Well, why don't I copy this entire system and say that, well, the Indian user would have a kind of leader like a primary DB in the Indian region itself, and it will just write to that, right? And it would drop the latency from 200 milliseconds to 2 milliseconds, right? And it could serve all the reads from all these replicas. Uh, so this is exactly what multi-leader systems are, right? Instead of having just one leader that is accepting writes, we could have multiple leaders, right, across different parts of the world or different data centers that can accept writes. Now you might ask, well, this looks good, then what's the problem here? So we'll come to that in the future. But just as a disclaimer, these systems are not really used a lot in real world. This creates more problems than it solves, right? And we will be discussing that in the video. Like, if why don't we use this massively on scale, right? So yeah, the use case is quite simple, right? We understand that, well, single leaders suck in the way that if that leader dies, what happens to our rights, right? We'll have to stop the system. If we have multiple leaders, those rights can go through those leaders themselves, the ones that are alive. So this solves that. This also solves the problem of scale. So we can deploy multiple leaders across different continents, and that would be great. The third thing is, of course, as I showed you, that it reduces latency a lot. We went from 200 milliseconds to 2 milliseconds. Of course, these are all hypothetical numbers, but yeah, you get the idea, right? Now let's talk about why they suck, basically. Okay. The reason for that is a single word, that is conflicts, right? If there are two kings, right, they would not really kind of agree with each other on a lot of different things. So for example, let's say I edit a column in a particular row of the DB on primary, and some user on the other hand does that on the same on this database. Like, who would win in that case, right? uh, what would happen, right? Would we drop this person's edit and accept the other ones, or what's gonna go on in that case? So this is something we will look in depth over here. And I want to talk about uh, where is this used really, right? So these architectures are usually used in applications where we kind of want instant writing, right? Or some applications where we want to have offline storage, right? Offline working, for example. Let's say there is a note taking app, right? You can, okay, now that app is your account is available on your phone and across your laptop, across anywhere else in the world as well, basically. Let's say you have a phone, you have some tablets, you have a computer. Your phone is now, let's say, disconnected, right, from the internet. You can write a document on your phone that would get saved on your phone itself. Your phone is behaving like this, like a primary DB of sorts, because it is, accepting writes. And then when your phone comes online, these writes are streamed across different databases, I mean different primary DBs all across the world. So that is one way where you need offline access, you can use this. Second is in places where there is not great connectivity. For example, you might have some rural places in Africa, for example. There's not great internet connectivity. You kind of want to write to your local DB, and only when you get connected to the internet, you write those things, your changes across to the actual DB itself. So yeah, now I told about the conflicts that can happen, right? A very real world example of this could be, let's say that you're Amazon, right? And you are keeping track of how many iPhones are there, for example. And there are two people. Let's say there's the same inventory all across the world, right? So this is the US and this is India. What would happen is that if there's only one iPhone left, and one iPhone left that's in both of these primary DBs, right? Or these replicas, because we read from replicas. Well, hypothetically, and this could be true as well in real life, both users across US and India could hypothetically do a checkout, right? Even if there's a single iPhone. And that is just because in that region's database, they think that they have one phone, right? So Amazon's good in this case. They would get money from both users, but it's pretty bad UX over here. So we kind of want to talk more about how we manage conflicts, right, in these databases, like how conflict management basically happens, because that is the only downside of multi-leader architectures. In real world, what usually happens is that the best way to actually avoid these conflicts, if you are using multi-leader databases, is to avoid them at the application level itself. So let's say that you are Google, right? And you have Google Docs and you're using multiple leaders at the same time. And of course, all people all across the world can edit the same doc at the same time. So yeah, this looks like a good application for multi-leader architecture. What would happen is that the application should kind of obtain some set of lock, right? So if a person, let's say in Sweden, is writing something to the doc, the application kind of maintains a lock, sends that data all across the world, Now when that lock is released by that DB, right, only then can someone from India or somewhere else write to that document or something, right? But if you do this, if you kind of apply a lock, then what's the point of using multi-leader databases at all? Because then you are kind of mimicking this latency, right? What if the user in India has to wait for, let's say, 2 seconds before that lock is released? That 2 seconds is more or less this latency, right? The only advantage of using one of the major advantages of using multi-leader databases is that you want instant replication. I'm sorry, you want instant writes, right? So doesn't make a lot of sense if you do if you apply locks on the system, right? um, Another way to kind of get to kind of solve conflicts is to kind of apply a timestamp, right? So let's say a user in US updates some sort of something in a DB, right? And the person in India is also updating the same thing. Now what would happen, one sec, yeah, now what would happen is that, let's say we give a timestamp to both of them, and whatever time whatever request comes, whatever request has the latest timestamp, we just allow that request, and we just reject the other request altogether. Sounds good on paper, but there are a lot of problems with this approach. Number one is that the person in US would not even know, like, where did their change go at all. Second is, clocks can be incoherent, and that's a big thing, right? How are we so sure? There is, first of all, there is no world clock as such. There is no absolute time, right? What if the clock that our Indian servers were using is kind of off by like 1 second or something, right? So in actuality, the person who made the request in the US was right, and our Indian person was behind, but because of the clock, their change got deployed and not the other person's. So yeah, that could be a problem, right? So we could use some sort of timing for that, but yeah, this is bad as well. Again, multiple ways to do this. You could use some sort of primary ID, you could use some sort of UID, right? You can generate IDs on a whim, and whatever ID is the latest by some algorithm that you kind of choose, and whatever right has the highest UID, you can kind of use that. But again, there can be exploits over here as well, the same that I told about timing and all. The second thing, um, the second way, so the first way is obviously to do it on the application level. The second way is what we called version vectoring. Okay, this is a kind of an advanced concept, but we'll just look at the surface of it, right? So I'll make a diagram that will help us learn more about this, right? Okay, so let's say we have a leader. Let's say we have a leader one, right? Let's make, now we have multiple leader databases, so let's make 3 leaders, or you know what, why not, let's make 4 leaders. Okay, and we have users. So let's say this is a user. Okay, I should decrease the font size. Yeah, so we have 2 users over here, because that's the whole idea, right? We want multiple users to kind of talk, I'm sorry, to use the same thing, right? We want them to be able to write to the same DB and all. So let's say we have 4 leaders. I'm not even talking about replicas over here, right? Also, of course, let's look over here. Once some user writes to this primary DB, those changes obviously have to travel all across the world and go to India, right? And those changes have to be written over here. Same goes for all the changes that you do in India, right? Whenever you make a change, that change should like go to your US's server and all, right? So yeah, let's now make, oh sorry, let's now make now this basically represents time. Okay, over here, okay, over here, and yeah, that's about it. Now let's kind of, I want to show you how these what problems can really happen, right? So user 1, let's make their queries in green. Okay, so user 1, let's say they write a query to, let's say, the user sets a query to add a new, basically set some value of some table, right? That's what the user has written. Okay, there's some query where you set the value of a table, set some row or some column value of that table, right? Now what should happen is that, one sec, yeah, what should happen is that this leader after some time is going to send an okay message back to the user, right? That yeah, your query was written in this leader. Okay, now this leader is also going to send that message to leader 2, right? That hey, user 1 change something on the DB. This leader is also going to send that query to leader, oh, why is it curly, to leader 3, right? And this leader is also going to send that update to leader 4. Now let's say leader 4 takes a long time to reach that. Okay, now we have some other user all across the world. Now these are different, assume these are different continents or something, right? So let's say that this is our second user, and this user is listening to updates on leader 3, right? And it saw that, well, someone added a new value of some table, some row in leader 3, and it wants to update that value, right? Let's make their changes in blue. So this user wrote an update to this leader. Okay, the leader 3 processed it for a while, and it sent back an okay message to the user, hey, that your update was okay, right? Cool. This leader will send that update text to the other leaders as well. So this goes over here, this goes over here, and this leader 3 is also going to send that update to leader 4. Now this is critical to understand. Leader 4, if you look at that, this is an update. Okay, one second. So this is an update call, right? And this green thing, this is actually a create call. So leader 4 actually got an update SQL query before it was even created. And this can cause problems, right, for leader 4. I mean, this is the kind of problems I was talking about in the beginning. In multi-leaders, things can happen out of time, right? There's network delays, there's all sorts of lags, right? And what should leader 4 do in this case? Should it just ignore this update call, or should it execute it? I mean, if you execute this call, you will of course get an error, but or should it store it and wait for this call from leader 1? Or how does it even know that leader 1, there is a call, right, that leader 1 has sent, and after that it should update it? So this is exactly where version vectors come into play. So version vectors is an entire topic of its own, but more or less what really happens is that, assume there's a vector, right? Vector on an array, if you want to call. So let's say there are going to be, let's make it red. So let's say there's going to be, the vector is going to contain 4 items, right? Let's make this large. So it's going to be L1. Okay, L1 is going to have a number, then it's going to be L2 is going to have a number, L3 has a number, and L4, sort of like a map. Okay, but this is a vector. Now what happened was, when this user A made a call to this leader 1 DB, and it got an okay message back, what happened is this created a vector in leader 1. So L1 would be 1 and L2 would be 0 in all cases, because in the beginning everything is going to be 0, right? So once this thing is created, okay, this vector is also sent to all other leaders at the same time, right? So when leader 2 gets it, it will see that, hey, L1 had an update, no updates on any other thing. So leader 2 will kind of store this information inside itself. Same for leader 3, same for leader 4. Okay, so if you talk about leader this user B updating leader 3, and it sent that update to leader 2, let's look at this time in particular, right? This time, what happened at this time was, leader 2 one second, Sorry, I think I'm not able to explain this properly. But okay, we had these vectors that all these leader got. This user wrote to leader 3. Leader 3 already had this vector, right? L1 is 1, L2 is so on and so forth. Now, this user wrote an update query, right, on the same thing that user A changed, right, on L1. So once it sent an update query, this would make a vector of its own. Let me copy this. Okay, this would actually send another vector, and over here it would be L1 is basically 2. Once it would send this, now this leader 3 is going to send this vector all across to all other leaders, right? That hey, I'm sending an update on L1's item, and you should basically execute it. Now once leader 2 gets it, leader 2 already had this vector, right, where L1 was 1, and the new update is L1 is 2. So leader 1 has all the updates before this new update, so it can just apply it. Same goes for leader 1. But in case of leader 4 got this vector before it got the first vector, right? And leader 4 would think that, hey, I need to apply this update, but the ID is 2, right? And I have no prior history before it. So there is something that I'm missing from leader 1 that I must get, and only after that I should apply this update. So it just waits for a while. It waits for a while till it gets this vector from leader 1, and once it gets this vector, it has the required history that it needs to execute the update query after the create query. So after it gets this, it basically runs this query again, and we are even. So this is how consistency basically works in multi-leader systems, right? And you can see that it is quite complex, right? Usually applications don't use this at all in real world. Even collaborative applications like Google Docs or something like that, or all other applications of that sort, I mean, they're all single leader applications in the end, right? Single leader is mostly, the most common architecture is single leader. Then we have leaderless applications that we'll discuss in the next video, and multi-leaders are only kind of used in not a lot of places, right? But in the places that I showed earlier, usually in cases where you have where you need offline functionality. So yeah, this is about it, and I hope that explains some doubts. And over the next video, we will learn about leaderless apps, right? And that would cover the entire replication kind of a concept. And after that, we'll move on to other concepts like sharding and all. So yeah, thank you.